right, well, thanks so much, Scott. So as Scott said, earthquakes is a good way to describe me. I'm going to leap right in and try and make an analogy between seismology and astronomy. So we learn about the universe by looking up at the heavens with telescopes. We learn about earthquakes by looking down with seismometers, principally, not only, but principally seismometers into the Earth. Of course, outer space, for the most part, is inaccessible. The Earth's interior is as well. So we're forced into this mode of remote sensing. It's obvious for astronomy, a little less obvious for seismology and geophysics. Nevertheless, that's what we do. We try to see into the Earth using seismic waves. Now, some people look at the structure of the Earth, the three-dimensional geologic structure, and maybe how it changes with time. I focus on faulting and earthquakes. So the seismic activity is illuminated by recently looking at very small earthquakes and finding more of those very small earthquakes to better illuminate active fault systems. So I'm going to continue with this analogy. This is the Carina Nebula. It's a gigantic nebula. It's in the southern hemisphere, so it's not as well known as like the Great Nebula in Orion. What's shown at the top is from a telescope, a ground-based telescope in Chile, is an image of that nebula and the stars and whatnot, zoomed in increasingly from left to right. What's shown below that is an image from the James Webb Space Telescope that came out last year, and it's just remarkably clear. Right? You can see the same general structure, but you can see it in much more detail. It's more sensitive. The mirror's plated in gold, so it reflects the infrared. You know, there's a lot of very expensive hardware that went into making that better image. I'd like to do the same with seismology and with monitoring earthquakes. So with earthquake monitoring, my goal here, that I'm going to talk about today at least, is to develop better earthquake catalogs. And I'm going to argue that we can blow that out of the water in terms of the resolution we can get with improved software, not hardware. Applied to earthquakes, not to the nebula, of course. Okay, so this is the 2016 Pawnee earthquake sequence. This is in central Oklahoma, as shown, north central Oklahoma is shown there. This is the USGS comprehensive catalog known as COMCAT. Each of those dots represents an earthquake. Those are almost entirely aftershocks. We're looking in map view, so we're looking down. They're color-coded by time. The time of the main shock was yellow, right, and here. So most of those are happening very close together in time. And you can see the distance scale on the lower right. Through processing the same data that went into developing this catalog, using better software, we can get an image that looks like this. So there are close to 2 orders of magnitude more earthquakes in this image. I'm convinced that this is better than the difference between ground-based and space-based telescopes in terms of the increase in resolution. You can see immediately that this sort of fuzzy trend of maybe 2 different directions is clearly seen at the large scale. It's also seen at every resolvable scale. So down to 2 smaller scales, that what we call conjugate faulting, 120 degrees between the 2 trends. It's due to the interaction of shear stress, which drives earthquakes, normal stress, which impedes earthquakes, under a coefficient of friction of about 0.6. This is what we expect. This is textbook. And we can get at this through deep learning. So I'm going to just very briefly describe some of what we do. This is published in 2019. Wei-Chung Zhu, former student who's now a professor at Berkeley, developed an automated way to pick the arrival times of P and S waves, the 2 fundamental kinds of waves that we use to locate earthquakes. So the input is the wiggles in a seismogram. We're fortunate in seismology. We have millions of labeled examples that we can train these models on, so we don't have to create our own labels. They're pre-labeled by expert analysts. The output is classification probability that it's a P wave or an S wave or noise. So it's a classification problem. We sort of engineer it so that classification probability peaks at the actual arrival time, and we can get that to within a few hundredths of a second. reliably. So we trained it on data from Northern California. We adapted a sort of standard UNet architecture that was developed, in this case, for identifying tissue type in medical images with some manipulation. It works just fine for segmenting seismological time series. That is the sort of wiggles I showed you last time. We apply that to continuous data, and we get many, many times more pics. And that's how we generated this image of the Pawnee earthquake. So all told, in Oklahoma, which is not really known for its earthquakes, over a 10-year time period, we found over 300,000 earthquakes. We actually found over 500,000, but only 300,000 were well recorded enough to be located accurately such that we could see the structure. So here's one example. I'm just going to scroll through these different sequences. You see the same sort of overall conjugate faulting. That lower left part of the Fairview sequence, that's a horsetail splay. Really beautiful example of that. Central Oklahoma is just riven with these faults, which, by the way, were not mapped or appreciated before this work. For some reason, in north central Oklahoma, they're sort of evenly spaced, a few kilometers apart, and they're predominantly in one trend and not the other, and on and on. So nearly all of these structures were previously unknown. They're telling us about the frictional properties of the faults that are failing. These are induced earthquakes. So these earthquakes are happening because fluid is being injected into the Earth's crust in Oklahoma. So we can contrast that with the picture from Eastern California. So the Ridgecrest earthquake in 2019, magnitude 7.1, Eastern California. See, the angles there are nearly right angles. So for some reason, it's the shear stress and with not much effect of the normal stress, apparently, that's driving those earthquakes. So that's an interesting contrast, and it's telling something about the mechanics of faulting at depth. With these machine learning models, there's always the question of how well they generalize to out-of-distribution data. So let's go to Italy. This is the earthquake sequence in the central Apennines from, it's a 1-year time period. We've got 900,000 earthquakes in our catalog. It's normal faulting, not strike-slip faulting. So in map view, it doesn't look, they're not nice lines. But we get, again, a much deeper catalog. We use deep learning to develop these catalogs, so we like to call them deep catalogs for short. But we've got a much clearer view of this very destructive earthquake sequence. By doing it, we just took the same model out of the box, not retrained for Italy, but it worked just fine because the waves are basically the same. More challenging application was a volcano in the southern Indian Ocean that recently erupted with 6 cubic kilometers of crust on the ocean floor. We applied our method to that sequence as well in collaboration with the French. We found these deep long period events as shown on the left. Those are at 35 kilometers depth, so much deeper than any earthquake in our training set. It's an oceanic setting, not continental, and a different period band that the earthquakes resonate in. These are earthquakes thought to be related to the movement of magmatic fluids at depth. You can see that red triangle in the upper right of the left panel is where the eruption actually occurred. And the Pahala Sill in Hawaii actually has a similar depth and a similar offset from the active eruption in Kilauea. The time dependence of these sequences is different. The shallow crustal volcanotectonic events are shown in green. They happen early. But the long period events at depth keep chugging along, and they're continuing to monitor this. And I should say that the French were the first, and as far as I know, they're the only group worldwide who have taken our results and used them operationally. So they're using them to monitor this volcano. They're using them to monitor earthquakes in the Horn of Africa. They're using it to monitor really, really dangerous volcanoes in the Lesser Antilles. Okay, here's a really interesting and unique situation. So after the 2011 earthquake, the Japanese ambitiously deployed a cabled system in the shallow mud of the seafloor and telemetered that data to land. So that what you're seeing here on the left, these are not earthquakes, they're instruments. And they're recording lots and lots of earthquakes offshore Japan. What's happening here is the Pacific plate is subducting underneath Japan. The size of the grams, as shown in the middle, are really ugly. I mean, they're in the shallow mud, and so it's very difficult to pick the times, but so we retrain our machine learning model, and we increase the number of earthquakes offshore where that cable is by a factor of 7. This is a $250 million facility, so we've, in a sense, added $1.5 billion worth of value just by training it. I'd be happy with a small fraction of that total. Tonga, Fiji, again, this is OBS data, so these are instruments that basically sink to the ocean floor, record for a year, and are then retrieved. Very expensive to do. Tonga, Fiji, what's happening, the earthquakes are color-coded by depth, and we're able to get more than a factor of 10 more earthquakes. It fills in the whole slab, going from shallow to deep. In the upper left area, that's Fiji. There are all kinds of shallow earthquakes that are completely absent in the standard catalog. So we get a much better view of earthquake activity, even from a one-year deployment. We've done the initial processing, the measurements to develop a 10 or 20-year catalog, 10,000 station years of data for Northern California. I'm confident we're going to come out with the initial version of that this year. We're going to have looks like about 8 times as many earthquakes as in the standard catalog. We've started a collaboration with institutions across the Pacific North America plate boundary to do this for the whole plate boundary. That's probably going to happen next year. So these are really diverse environments, geologically diverse environments we've done this in, and it's with some modifications in places we've been able to do it everywhere or anywhere. And I'd like to argue that we can do it everywhere. So this is the EarthScope archive. It's data from around the world. And these arrows, actually, they got messed up. They're pointing sometimes to the wrong thing. But the point is there's domestic U.S. data. There's also a lot of international data, including temporary deployments in really interesting areas that typically last 2 years. Well, we can get 10 times as many earthquakes out of those, so it's like 20 years worth of data, at least in some sense, in terms of small earthquakes. So we can really make a lot of hay out of this internationally by mining this archive. It's less than a petabyte of data, so it's a lot of data, but it's not prohibitively large amount of data, especially because we have a cloud-based workflow that's containerized, it's cloud platform independent. All of these processes, except for the end, the joint location at the end, are embarrassingly parallel, which sounds like a bad thing, but it's actually a good thing because it means we can run them independently and just throw as many processors as we need to analyze the data efficiently. It can run on archives. It can also run in real time. So Wei Zhangzhu, when he was a grad student here, he was monitoring earthquakes on the big island of Hawaii in real time from the 4th floor of the Mitchell building. Okay, so I will assert that we could do this everywhere, not just anywhere. We'll start with data in the EarthScope archive. That includes the sparse global coverage and dense local coverage in interesting parts of the world. There's a lot of data that exists that's not there. It's in other repositories or it's not shared. I think there's an opportunity here to set ourselves up to sort of provide a service or to get people to get with a program and realize the benefits of these new methods. Everyone will benefit from that. I think this would revolutionize earthquake science, giving us a much clearer view of what's going on down there, just as the space-based telescopes do for astronomy. And it's highly sustainability relevant because earthquakes have put the clamps on enhanced geothermal power generation, nuclear power, and potentially carbon dioxide sequestration. So with that, I will thank you and take any questions.